Welcome everyone, and thanks for joining our webcast today. My name is Pete. I'm with Advanced Navigation and Positioning Corporation, or ANPC, and today we're going to be discussing the Instrument Landing System, commonly known as the ILS. For more than 60 years now, the ILS has enabled countless thousands of safe landings in weather that otherwise would have made landing impossible or at least delayed. It is a critical component of aerospace systems around the world and has resulted in the incredible air travel and transport capabilities that we now all rely on. Yet thousands of airports around the world have been unable to take advantage of this because of limitations in the conventional ILS system. Specifically, the ILS has strict sighting criteria that cannot be met where there are obstacles or rugged terrain surrounding the airfield. With its Transponder Landing System, or TLS, and Transportable TLS, or TTLS, ANPC has taken this technology a step further to provide precision approach guidance, that is horizontal and vertical guidance, to pilots in airports around the world where other systems cannot. Furthermore, these systems provide highly accurate terminal surveillance and tracking of all IFR-equipped aircraft within 120 nautical miles of any airport. So it's providing a virtual airport in a box for new, existing, and temporary airfields. So with that said, I'd like to introduce our subject matter expert today, Mr. Nelson Spohnheimer. Nelson is a former engineer with the Federal Aviation Administration, FAA, and has been testing and commissioning ILS systems for nearly half a century now. Welcome, Nelson. Good morning, and thank you very much for joining us. Why don't you tell us a little bit about yourself and your experience?
Thanks, Pete. I'm a retired FAA engineer, retired in 2005. I spent 31 years with the FAA. Before that, I spent about 7 years in industry, which included 5 with Texas Instruments, and that's where I started on my ILS experience. We won the contract for the initial Air Force Cat 2 program, which was later embellished to include FAA Cat 2s. And I went to most Air Force bases and commissioned a lot of facilities. After I joined the FAA, I continued doing the same sort of work and branched out into VOR and TACAN and DME, some of the other ground-based navigational aids. And this is now my 49th year since my first ILS commissioning.
Wow, that's fantastic and pretty impressive. So Nelson, if you can give us some background on what an ILS is, how the quote-unquote conventional ILS functions, and what its impact has been on the industry, that would be a good place to start.
ILS stands for Instrument Landing System, which is an internationally defined navigational aid. Today, they support Category 1, 2, and 3 approaches. Category 1 approaches take the aircraft down to about 200 feet, as low as 200 feet above the runway. Category 2 is as low as 100 feet, and Category 3 has several sub-flavors, but can take the aircraft all the way to touchdown without the pilot being able to see in low visibility. Typically, they have 2 components, 2 primary components. The localizer provides right-left guidance. The glide slope provides up-down guidance. Often co-installed as ancillary aids are distance measuring equipment, DME, some fan markers, which are 75 megahertz upward directed beacons prior to the runway, let the pilot know in crude terms how far to the runway, to the runway. And they have various monitors and remote status indicators at control towers and so on. So the entire system usually comprises localizer, glide slope, distance measuring equipment, and the remote control and status indicators. The localizer operates in the VHF frequency band and provides signals out to 35 degrees either side of the runway, out to typically 17 to 25 miles, depending on the local environment. The glide slope operates in the UHF frequency band and provides signals out to 10 to 17 or 20 miles typically, again, depending on the local environment. The localizer antenna system is located beyond the stop end of the runway so that it can provide guidance down the runway in the case of Cat 3. The glide slope is located near the approach threshold off to the side, roughly a beam the touchdown point.
So you say the localizer antennas must be located beyond the departure end of the runway. Is that to maintain a standard course width at the approach end, the threshold?
Well, it does imply indeed that there is a width to the localizer, the active proportional part of the fly right, fly left guidance is called the course width. It's the angular distance between full scale right and left deflections on the cockpit indicator. And it's generally 3 to 6 degrees wide, depending on the runway length. Internationally, the width of the localizer is standardized so that at the approach threshold, if the aircraft is 350 feet either side of runway centerline, the needle just fully deflects full scale, either right or left. That way, the approach feels the same near the landing point for each runway. You go from a short runway to a long runway, all of them are set up nominally so that 350 feet either side of the approach threshold, you see full scale deflection. So you have a standard sense of how aggressively you must move the aircraft, right or left, to get to the center line.
So doing some basic math, this means that to achieve that required course width of 700 feet at the runway threshold, the localizer antennas need to be located more than 2,000 meters away, which is past the departure end of many runways. And while this is fine at airports with long runways and graded terrain at the departure end, it presents a problem at airports with shorter runways and roads, water, buildings, or other obstacles near that end of the runway. So at many such locations, a conventional ILS cannot feasibly even be installed. And the same is true on the arrival end, where marker beacons are typically installed as far as 7 nautical miles away from the airfield. So Nelson, if we're talking about a Category 1 precision approach, which is what the TLS is offering, what are the general requirements of a system providing that kind of approach as far as ICAO is concerned? ICAO being the International Civil Aviation Organization formed by the United Nations to establish global aviation standards.
Yeah, ICAO specifies, I call them the 4 big nouns: accuracy, continuity, integrity, and availability. The first 3 are generally dealing with signal and space, while the last one, availability, is an economic question for many airports. So for Category 1 equipment, the approaches have to have a certain smoothness to the guidance, and that varies with category and distance from the runway, and that applies to both localizer and glide slope. So the guidance is never a purely straight line because of reflections and noise, electrical noise, and so on. So there's a limit placed on how much error is allowed along the approach course in both right-left guidance and up-down guidance. There are numerical values required for integrity, which is a measure of how confident the user can be that the signals are correct and aligned as they should be, and so on. And that's specified in probability of having a poor signal on the air when it shouldn't be. And finally, the continuity is specified in mean time between outages generally. How likely is it that once you start an approach, the signals will remain on the air for the duration of the approach? So those 3 big concepts are specified in numerous pages of details in the international documentation.
Okay, thanks, Nelson. How about a deeper dive on how those localizer and glide slope signals, guidance signals, are provided by an ILS and how they are interpreted in the aircraft?
Okay, very well. Each of the localizer and glide slope subsystems has an antenna array comprising 2 to 20, commonly, antenna elements. The localizer in the US is commonly 8 or 14 or 20 elements, which look a little like your older outdoor TV antenna. Each element is a multi-element antenna, and they work together to provide a certain shaped pattern in the plus or minus 35 degrees azimuth space centered on the runway centerline. So they radiate a static field, and in any passive receiver that's brought into that field, radiated field, will indicate a right or left deflection that's proportional to the aircraft's position, if it's within the course width, the 6 degrees or so, 3 degrees on either side of the runway. If the aircraft is outside that narrower wedge of proportional guidance, the needle is pegged full scale all the way out to 35 degrees either side of the runway center line. So the science of localizers these days is pretty much dealing with how well the antenna patterns fit the environment. Provide energy no more than out to 35 degrees either side, preferably dropping fast beyond that, and not illuminating large objects such as hangars on the airfield or power lines that might be parallel to the runway center line, because those objects contaminate the smoothness of the guidance. Similarly, the glide slope has 2 or 3 antennas arrayed vertically on a tower that might be 40 to 50 feet tall, about 400 feet either side of the runway, one side or the other. And those antennas radiate signals directly to the aircraft, and they also bounce them off the ground in front of the antenna system, which necessitates a reasonably sized prepared area where the ground is sufficiently smooth and has sufficient extent to support the desired ground reflections. These 2 signals directly to the aircraft and off the ground combine to create the static field in the vertical dimension, much the way that the localizer provides a static field in the horizontal dimension. And again, any passive receiver, a non-emitting receiver, a non-participating aircraft, so to speak, that's brought into the glide slope radiated field will receive signals deflecting the needle up and down, proportional to how much the aircraft must be moved to get to the desired approach angle, which is usually 3 degrees for large aircraft. So those are the key characteristics. You have a static field radiated by multiple antennas in an array for each of the localizer and glide slopes, and the static field has the characteristics that the needle is deflected right or left or up or down in a proportional manner to keep the aircraft centered along the approach path.
So, well, that's a good lead-in then to the TLS, which I know you have some first-hand experience with. Of course, the TLS is being marketed first and foremost as a fully compliant Cat 1 system per ICAO's requirements, but the underlying architecture is quite different, isn't it?
That's correct. Once an aircraft has started a TLS approach, it flies just like an ILS, and the signals that are emitted by the ground station comply with ICAO requirements in the sense of smoothness and signal strength and various other parameters. But the architecture of generating that signal is quite different. It's based on the aircraft emitting a standard signal from its radar beacon transponder, and the arrival angles and times of the emitted signals are used to determine where is the aircraft at this instant. And then the field that's radiated on the localizer and glide slope frequencies is dynamically changed so that you get the same needle deflections on a TLS approaching aircraft as you would an ILS. So in this case, the field is not static, it's dynamic, unlike the ILS, and the aircraft has to be emitting a signal. Those are the 2 fundamental differences.
And you talked about the ground in front of the glide slope antenna creating a reflection that is important to the formation of that signal. This is perhaps a good point to express how TLS has the ability to model that ground bounce because the TLS is receiving the signal from the transponder that reflects off of that ground, and we're able to calibrate the effect of that ground bounce, correct?
As I mentioned, the aircraft is emitting its standard beacon pulses, which are in the L band or around 1,000 megahertz. And that has several implications. One is that the sensors, the TLS sensors on the ground, can use antennas at a much shorter wavelength than ILS antennas. And that means that the antennas used can have vertical sensitivity. They can have a negative cutoff. They are not very sensitive to signals arriving from the aircraft that grounds off the bound in front of the TLS sensor. But the attenuation of signals is not complete, so there's still some ground bounce. And that means that, or it turns out that you can measure the characteristics of the site for these reflections from the ground in front of the TLS sensor, and you can subtract out the effects effectively of those reflections for all subsequent approaches. Once the TLS is calibrated for the site, then the effects of the ground bounce are effectively removed.
So Nelson, if I can summarize, you're saying that the TLS antennas are less sensitive to vertical multipath interference in the first place, but because it's calibrated specifically to the surrounding environment and knows the precise location of the aircraft at any given time, the TLS is able to compensate for any potential reflection-based errors dynamically and in real time, which is unique and pretty exciting. So getting back to equipment sighting, the TLS localizer is not actually located on center line at the far end of the runway or beyond. On a TLS approach, that point in space is a virtual emanation point. That is the point in space where the signal appears to emanate from, even though all TLS components, including the localizer antenna, are co-located near the threshold at the approach end. So can you tell us a bit more about how that creates a localizer that appears like any other one?
Since the TLS sensor is receiving signals from the aircraft, which are normally transmitted for surveillance purposes, and using those to determine the position of the aircraft, it's a simple calculation to determine what sort of needle movement should be seen in the cockpit if this were a conventional ILS. And that needle movement signal need only come from a single antenna, unlike the typical localizer glide slope where you have multiple antennas to create a field that has certain needle deflection characteristics. Now only a single antenna that covers the full service volume is needed, since the deflection, the amount of deflection that's desired to steer the aircraft correctly comes from a single source, and that source can be located anywhere around the airfield that satisfies the need to get the signal to the aircraft. So in the TLS case, the azimuth and elevation stations are both in a common area near the approach threshold, rather than being a mile or two apart.
So this really is the secret sauce, isn't it? And it's what created the market for TLS in the first place. We're not really targeting airports where a traditional ILS is even feasible without major civil works and expense, if at all. The TLS could emanate an ILS localizer, glide slope, and marker beacons without installing physical hardware outside of a small footprint near the runway threshold or astride the runway. So Nelson, can you talk a bit more about the significance of this capability in terms of being able to serve more airports?
Surely, an ILS, a traditional ILS, does require can be some expensive site prep, or maybe not terribly expensive, but because there are subsystems scattered about the airfield, there's multiple sites that have to be prepared and leased and have connectivity and so on. And by bringing all the components together near the approach threshold, there's just one site that needs to be prepared. We spoke earlier about how the elevation sensors, antennas, have substantial vertical directivity and therefore aren't too sensitive to ground bounce in front of the antennas. That means the site prep is less extensive. The area that has to be smoothed out, which is normally a signal generation problem for a classic glide slope, are greatly reduced, and so the amount of space that's required on the airfield to protect the antennas and allow them to generate the correct characteristics is smaller. It's also at L-band frequencies instead of VHF and UHF, and it's just a single site. So collectively, those things mean that a TLS can be installed at some airports where it would be a real challenge to prepare the sites for traditional ILS. And even at some sites where the reflection environment, the multipath environment, might be too challenging to get a given category of operation with an ILS. Most ILS sites have been successfully installed at really tough spots, but some of them are quite expensive.
And not just installation costs, but maintenance, flight inspection, and so forth. Is that right?
Well, yes, there's recurring maintenance, typically periodic and sometimes as needed schedules. The manufacturers propose schedules for the nature of the equipment. Today's modern ILS equipment just requires a few hours a quarter, as long as the gear continues operating fine. The periodic checks are relatively simple, but do require a quarterly on-site visit. The monthly things can be done remotely, generally. Flight inspections in the U.S. occur every 18 months on an ILS. And each one of them has a test of the monitor. So it's a flight inspection that goes beyond just examining the radiated signals. It also looks at the ability of the monitor system to turn the gear off before it gets too far out of shape, should a failure occur in the electronics or the antennas. But generally, a Category 1 recurring monitor's flight inspection might take half a day, up to half a day or so. Commissioning flight inspections are much more extensive and might be a day or two for a Cat 1, longer for Cat 2 and Cat 3.
Nelson, what's the driver behind the required 18-month interval between flight checks?
Well, that interval has stretched out over the decades that I'm familiar with. In earlier days, equipment was tube type or first generation solid state and a little more prone to drift and had less reliability than modern electronics do. And therefore, flight inspections were deemed to be needed more frequently. They were as often as every 6 months. And as the generations of equipment matured and new gear was fielded, going from tube type to solid state point-to-point wiring to circuit boards to microprocessor-based control and so on, the reliability of the gear has gotten better. And similarly, the test equipment used to maintain the gear has gotten better. And as a result, the flight inspection folks who watch for failure modes and frequencies of problems and so on concluded that they could stretch out the flight inspection intervals because the gear was more reliable. So that's grown. It went to 9 months and then to 18, where we are now. And that's pretty much true as a concept internationally. The intervals may not be exactly the same in other countries, but they've all been stretching out. Flight hour costs are, of course, extensive for an aircraft, and reducing that is a side benefit. But in general, the equipment on the ground has gotten good enough compared to decades ago that there's no need for quite as frequent flight inspections.
So our TLS product manager, Carl Winter, tells me that we can make a very strong case for even longer intervals between TLS flight inspections. Its calibration and built-in test gear monitor the aircraft and all key performance parameters involved with its location. So the alignment of the guidance signals are also being monitored continually.
Well, if I may elaborate just a bit, Carl's point is that because the TLS has an architecture that has a dynamic field, radiated field, and because the aircraft is emitting a standard signal, the transponder signal, it's feasible to put a small transponder, in other words, an unmovable aircraft, in front of the TLS sensors, such that it looks like a parrot in radar terms. It's a reliable source that's at a known location, and the TLS can listen to that emitter that's in front of it, the artificial aircraft, so to speak, and confirm that it remains in the same place, it's sensed to be in the same place, and therefore the guidance that would be generated for an aircraft at that location would be constant over time. And by that method, the parrot, the artificial aircraft, so to speak, that's in front of the ground sensors and stationary, is a reliable source to confirm that the computations in the TLS, that the reception, the algorithms that determine where is the aircraft are all constant and as they should be. So this is a benefit that's not so obvious in comparison with ILS. Category 1 ILSs generally don't have that advantage where they have an equivalent of an aircraft receiver in front of the system constantly checking its appropriateness for its radiation. Now, Cat 3 ILSs do that with something called the far field monitor, a sensor that's at the far end of the runway that validates that the localizer is still radiating its course line in the correct location. But this is true for all of the TLS installations with an active monitor, basically.
And with regard to the applicability of flight inspections, the FAA does maintain a current order, Order 8200.47, for flight inspection of the TLS.
Yes, internationally there is a manual for testing of radio navigation aids. It's called Doc 8071. And for ILS in particular, it defines the parameters that are typically tested by a regulator, let's say, on a periodic basis, both in the air and on the ground. Now, some parameters cannot be checked on the ground. For example, alignment, which is the airborne average in the last mile of the approach on a localizer, for example, can't realistically be checked on the ground. So an aircraft is required. So the U.S. Flight Inspection Manual elaborates quite a bit on the international one and lists in very crude numbers, I haven't counted lately, let's say 20 or so parameters that are checked with the aircraft. Course width, signal strength, alignment, smoothness of the guidance, and so on. And then similarly, there are some ground checks that are done with ground test equipment on a traditional ILS. Now the TLS, because it has a dynamic field radiated from a single antenna, doesn't need to have a flight test of the course width because that's done with calculations. It doesn't need to have as rigorous a check generally on smoothness of the guidance because errors along the guidance path are calibrated out with test flights before the commissioning is established. And parameters such as modulation percentage and RF power and so on are checked on the ground. So it's a little bit lighter load if you carefully look at what requires airborne testing versus ground in the ILS case versus the TLS case. Because one has a multi-element array, which has more failure modes that have to be tested with a monitor. The TLS has a single radiating antenna for each of the localizer and glide slope systems. So there aren't as many failure modes that can occur in the outdoor equipment. So the flight inspection workload list, so to speak, has fewer steps to check for the failure modes.
Do you have any ground checks to monitor? The ILS gets ground checks from the monitor, and some folks have looked at TLS for similar ground checks.
You were speaking about the ground checks that are required for traditional ILS, which are to measure on the ground the course position at the approach threshold, let's say for the localizer, to measure the course width, to see if you have full-scale deflection 350 feet either side. Those steps are repeated with an airplane, but repeated in such a way that the alignment is an average of a mile of flight, which is a part that you can't replicate on the ground. Ground checks for the ILS also, because it's a multi-element array for the localizer with 8 or 14 elements generally, we'll look at a spot on either side of the runway center line where the guidance most quickly deteriorates, called the low clearance point. Again, that is required or deemed to be required because there are failure modes in a multi-element array that might not affect the course line, but can affect the deflection of the needle either side. Again, that particular issue doesn't occur for the TLS because it has a dynamic field that's radiated from a single antenna. So again, it's the issue of what are the failure modes that have to be tested, how rigorously does the monitor need to be checked to see that it will catch failure modes. If there are fewer failure modes from the radiating antenna system, then it follows that there are fewer checks that have to be flown.
Okay, great. Well, we won't go too much longer here, Nelson, but do you have any thoughts on the future of ground-based nav aids given ICAO's PBN or performance-based navigation initiative or the FAA's next generation model and similar aviation initiatives? I know they've been talking for 20 plus years about replacing ILSs and getting rid of all the orange and white boxes a long time ago in favor of satellite-based solutions like GBAS and WAAS. But of course that hasn't happened, and I'm not sure it ever will. What are your thoughts on that?
My thoughts are not a lot different than most of the industry. The FAA was hopeful, of course, in the early days of GPS that all ground-based equipment could be turned off and a lot of savings could be accrued for both maintenance and installation. But the issue of having a backup for a GPS system-wide or area-wide outage remained, and some major studies by universities were chartered by Congress, and the result was that we have to retain some modicum of ground-based equipment for wholesale GPS outage. The current FAA plans are to retain ILS for Cat 2 and 3 for the indefinite future, but that Cat 1 landings will be largely supported by AreaNav or RNAV, GPS WAAS based systems, and something like the numbers vary at the moment, but something like half of the Cat 1 ILSs could conceivably be turned off. And there's a program to rationalize which ones, to determine which ones, much like the VORs are being thinned. The proposal is to thin the Cat 1 installations down to a enough lesser number that there's some good savings from maintenance. RNAV approaches are published in most every airport that has an ILS and many more that don't. And as equipage has grown, there's no doubt that Cat 1 landings operations can be supported by GPS loss, except for the rare case that there's either interference or a solar storm or an outage of the GPS equipment itself or the ground control segment, each of which is relatively rare. But if they occur over a wide area and affect a lot of airplanes instead of a single runway at a single airport like an ILS outage would. So it appears that Cat 1 ILS will be retained at, very crudely speaking, something like half, 50–60% of the sites.
So even with all the augmentations and improvements, GPS outages are not going to go away altogether anytime soon, unless we find a way to control space weather events and so forth, correct?
Well, that's true. The occurrences are rare, but a major sunspot, solar storm, solar eruption, or intentional, unintentional RF interference on the ground are the weak spots for GPS because the signals are weak. They perform beautifully as long as they're receivable, but things that would disrupt reception, such as I've mentioned, are the concern, and that's why nationally there's an effort to define a backup to GPS that's sponsored nationwide. And unless that comes along, FAA's plans appear to be to retain some number of traditional ground-based nav aids. The number's not very solid just yet, but if we say we have 800 or so Cat 1 ILSs, maybe 500 might remain.
Certainly, and we see TLS as a viable component of that backup plan for airports that never had an ILS to begin with. So I want to turn now to the approach design procedure and the applicability of PANS ops and TERPS criteria for designing TLS approaches. Can you elaborate a little bit?
Well, PANS ops is the name that ICAO uses for their document that defines how to design instrument approach procedures. In the US, it's called TERPS, Terminal Instrument Procedures. And both of these documents define imaginary surfaces that must be clear of obstacles. They define pieces of airspace, which have to have certain characteristics so that the aircraft, when flying a nav aid of known accuracy, can assure sufficient obstacle clearance and terrain clearance. Since the TLS is flown flight tested against full-up ILS signal and space performance characteristics, functionally and conceptually, it should be fine to use ILS procedure design rules for a TLS approach. It behaves in all radiated purposes the same as a Cat 1. At least it complies with the published ICAO requirements for Category 1. It has different characteristics that we've discussed, but from a user point of view, it's the same signal and space. So PANS ops or TERPS Cat 1 criteria should be usable. The US did agree, the FAA agreed that TERPS would be used for TLS approaches in the US.
Thanks, Nelson. One final point I want to mention is in regard to our TTLS Transportable TLS, which functions identically to the fixed-base TLS, but can be repackaged in a variety of configurations to be rapidly deployable and redeployable to temporary or remote airfields by expeditionary forces, humanitarian relief, or emergency response organizations. In such installations, a TTLS not only provides precision approach guidance, but highly accurate secondary surveillance and primary approach radar capabilities to maintain separations, full situational awareness, and safe landings in all weather conditions. So it's really a full tactical ATC solution. And these systems can be installed or uninstalled in a matter of hours in almost any environment and don't require concrete pads or footings or any civil works that are required by other systems. So that's our talk for today, folks. I hope you all found it informative, and please contact us via email or phone at the contact info below with any comments or inquiries. We'd love to hear from you. Nelson Spohnheimer, thank you very much for your time and insight today. This is all very useful information, and we greatly appreciate your perspective and your expertise as always. So take good care until next time.